Hello everyone, it's my honor to have the opportunity of making this presentation. My name is Mengmeng. I come from Suzhou University in China, and I'm here on behalf of the first author, Wenbo, to report for you. Mm, and to, my topic is today. My topic is our novel 16-sided cobweb-like disc Resonator Gyroscope with low as-fabricated frequency split between drive and sense modes. Next, I will introduce my topic from the following aspects. Firstly, I will talk about the background of gyroscope, and secondly, some details about cobweb-like disc Resonator Gyroscope will be introduced. Thirdly, there will be some comparison between ring-like DRG and cobweb-like DRG, and then I will show some measurement results. Finally, the conclusion and acknowledgement will be included at the end of this presentation. As we all know, MEMS gyroscope is an important inertial sensor, which is widely used in consumer electronics, robots, automobiles, and military fields because of its small size, low cost, and batch production. And the following figure is two structures of ring-like disc Resonator gyroscope. Afterwards, I will call it ring-like DRG for short. In recent years, the ring-like DRG has attracted much attention due to its favorable features, such as high thermal stability, large transducer area, low anchor loss, and capability to work at whole angle and force to rebalance modes. However, there still exist problems. Frequency split caused by inevitable manufacturing error will reduce the performance of gyroscope. In order to reduce the frequency split, there are several methods to improve the structure symmetry and to compensate for the fabrication errors. One common way is electrostatic tuning, but sometimes it needs high voltage or large size electrodes. When voltage is too high, it may cause quality factor reduction. Another way is to add or remove materials at a specific location on resonator as shown in the red figures. The stiffness and the mass distribution is modified and the quality factor is optimized. However, this method always requires post-processing steps and it's very complicated and time-consuming. In this work, we proposed our new asymmetric resonator structure, as shown in the first figure. Instead of circular ring in conventional ring-like DRG, in traditional ring-like DRG, we designed a 16-sided cobweb-like disc resonator gyroscope. It seems to have a better tolerance uh, to crystal orientation error and fabrication errors, such as sidewall at angle. As a result, it has low as fabricated frequency split compared with the traditional ring-like DRG. And here is the same photos and its structure dimensions. The perimeter, it consists of 10 concentric 16-sided cobweb rings. They are connected through 8 alternating spokes. And our lambda mass is added to enhance the effective mass and the quality factor. Besides, this resonator is surrounded by 16 external electrodes for electrostatic tuning. Below it is the drive and the sense mode shapes, and from the TED analysis, we know that the ideal frequency is about 18,000 2000 Hz, and the ideal quality factor is about 213,000. Wafer fabrication process starts with our SOI wafer. First, etch a shallow cavity and bottom electrodes, and then bond the wafer with another SOI wafer, which is also called device wafer. Next, remove the substrate silicon of device wafer and release the proof mass structure by deep reaction and etching, followed by metallization. This step, the device wafer is hermetically sealed by a cap wafer with getter using a As-Fabricated bonding method in vacuum. The characteristic tests have been carried out for the cobweb-like DRG, and the first figure is the detection circuit. The frequency response test results show that the frequency split between drive and sense modes is only 0.56 Hz, and delta frequency over frequency which indicates a relative frequency error is about 29.9 parts per million. And this split value can be reduced to 0.01 Hz by applying DC voltages, and the relative frequency error is about 0.5 parts per million at this time. The random test results show that the quality factor of both drive and sense modes are all more than 112,000, and the delta of 1 over 2 is about 3 millihertz. In order to compare frequency split behavior, we place ring-like DRG and cobweb-like DRG side by side on this wafer, and the 5 pairs are tested. The results are listed in the table here. It's found that the relative frequency error of ring-like DRG is about 7.4 times larger than that of cobweb-like DRG. That means that the cobweb-like DRG has a better symmetry compared with ring-like DRG. And in order to explain this phenomenon, we carried out simulations in COMSOL. And in COMSOL, we carried out simulations in COMSOL to explore the influence of crystal orientation error and etch angle error on frequency split, and the results are shown in 2 figures. The left figure shows the relative frequency error caused by crystal orientation error, and the right figure shows the frequency split versus etch angle error. The right line is ring-like DRG, and the blue line is cobweb-like DRG. From these 2 figures, we can see that the blue line is always lower than the red line. That means the symmetry of cobweb-like DRG is less sensitive to crystal orientation error and etch angle error. The performance test result indicates that our gyroscope achieves a scale factor of 19.1 millivoltage per degree per second at the range of minus 200 to 200 degrees per second, and the island deviation of zero rate output is calculated. The result shows that the angle random walk is 0.1 degree per square hour, and the phase instability is 0.75 degree per hour. Well, that's about it. To summarize, I have talked about our novel 16-sided cobweb-like disk Resonator Gyroscope is proposed, and it's mirrored as fabrication frequency split is 0.56 Hz, which means relative frequency error is 29.9 parts per million, and the split value can be reduced to 0.01 Hz by electrostatic tuning. And the mirrored scale factor is 19.1 millivoltage per degree per second. Algorithm work is 0.1 degree per square hour, and their instability is 0.75 degree per hour. That's all. Thank you for your attention.